Okay, let's take a look at an example problem that uses some of these insights that we've gained about the impulse response and the step response and relationship between rise time and bandwidth and so on. So in this problem, we're given that we're trying to transmit data at a rate of 1 million pulses per second down a particular communication channel, and we're shown the step response of the channel. Primary information that we get from the step response is that the rise time is 10 to the minus 5 seconds or 10 microseconds. Okay. And then based on the material in section 2.7, we also know that this is the effective time constant for this particular system, that they're approximately equal. And in part A of this problem, we're asked to see if the channel can transmit data at the required rate. So we actually want to compare R here to the reciprocal of the rise time, and the reciprocal of the rise time in this case would be 100 kilopulses per second, or 100 kilohertz. But since the data rate which we're trying to transmit data down the channel is greater than 1 over TR, we would expect pulse distortion to occur. In fact, there should be pretty significant intersymbol interference. So in answer to the question, no, the channel cannot transmit data at the required rate. We need for R to be less than 1 over TR in order to avoid the distortion. And in part B, we're given a different problem. Here we're talking about transmitting audio data with a maximum frequency of 15 kilohertz down this channel. And again, we're asked, can this channel handle the data again without significant distortion? Here we want to compare the maximum signal frequency to the channel bandwidth. Again, the channel bandwidth is related to the system time constant. It's the reciprocal of the system time constant, and that is 100 kilohertz. Now, since F max is less than the channel bandwidth, no distortion. And in part A, there is distortion. Okay. I'm going to take a look at this actually. Let me clear the page here. I'm going to take a look at this in Ltspice. We'll set up an Ltspice. So here I've got a square wave, a pulse train generator that's generating pulses actually with a period of 1 microsecond or 1 million pulses per second. And I've set up 3 separate filters that simulate this low pass channel. So we're in the problem, we're given that the time constant is 10 microseconds. So the output of that filter with this square wave input is y1, and then I look at reducing the time constant. So now if we simulate this case, okay, here at the top in the green you see the input pulse. Again, there's the input pulse train has a period of 1 microsecond. And here's what happens when we send that pulse train through the channel that has the long system time constant. What happens here is the channel acts very much like a low-pass filter, and then the output here is steadily climbing. It should eventually reach 2.5 volts, which is it's less than that based on the duty cycle. But it should steadily climb until it reaches the average value of this particular waveform. And it doesn't look much like the original waveform at all, so there's significant channel distortion. It would be pretty difficult to actually detect the peaks. We can do it visually. You can see where the peaks are actually in this particular waveform, but if noise is present, it's going to be hard to detect this with any sort of threshold detector with any reliability. And then here I've reduced the time constant by a factor of 10. I think it's 1 microsecond. Again, fairly significant distortion of the original waveform. Here I've reduced it further, again by a factor of 10. Now we start to see the individual pulses. Again, there's fairly significant pulse distortion and pulse spread. You see how this narrow pulse is now much wider. And then finally, in this last case, this is where the time constant is 0.01 microseconds. And this is a fast system. Of course, that term is relative. It's fast relative to this input signal that has a period of 1 microsecond. So in this fast system, we see the output pulse train looks very similar to the input pulse train actually. So there is some distortion, that's always going to be present, but we can clearly see the pulses in this particular case. You can do a similar simulation actually in octave. So here define the pulse train, actually first define one period of the pulse, and then use the gen per function to make it periodic. And then actually here I define the impulse response of the system, and then step through again 4 different impulse response values going from 10 microseconds down to 0.01 microseconds, just as was done in the Ltspice simulation. And use CT-conv to convolve the input with each of these the impulse response, and with the 4 different time constant values. And this is the result from that simulation, again showing the input waveform at the top, and then the resulting output at the in these 4 graphs right below the graph of the input. The results here are very similar to the results we got with Ltspice, and of course they should be if both simulations are correct.